Welcome back to the lecture series on analog electronics. This lecture series is a part of Let's Crack the Gate initiative by TEQIP Faculties. Today, we are going to discuss about BJT transistor modeling. This is the first part of small signal analysis. We will model the transistor and then we will apply the small signal analysis. Okay, so this model can be called a small signal model of transistor. And now you might be wondering about what is the small signal. Is there a large signal, right? So small signal means we know that our input signal is of very low magnitude most of the cases, right? So if we want to analyze our amplifier for those smaller signals, we need to apply small signal model. And in this small signal analysis, we have two types. Let me write that down. There is small signal analysis, and it is done for low frequency signals as well as high frequency signals. Then there is large signal analysis that we will do later, and there is no clear-cut division between this small signal and large signal. What is termed as small signal or what is termed as large signal, there is no defining line between these two. It depends on our application. For what application we are using this transistor, regarding that, this small signal and large signal, this changes. So if our applied signal is small, we can assume that our transistor inside its operating region is linear. That amplifier is linear. I've told you that there is low frequency and high frequency models in small signal analysis. For low frequency signals, we use these three models. One called pi model, then one called T model, and the last one called H parameter model. Okay, and for high frequency signals, we use these two models, which is pi model and T model. You remember the R pi and RE we derived in the last lecture. So in pi model, we use those relationships, that is, we use R pi. So this model can also be called R pi model. In T model, we use RE. So this model can be called RE model. Then there is H parameter model or hybrid equivalent parameter model. You might have learned about this in two-port networks in network theory. And in high frequency, we use pi and T model, which is the same as in here. Now we know the equation for R pi. R pi can be written as VBE divided by IB, or that can be written as beta divided by GM. Now RE can be written as VBE divided by IE, or alpha divided by GM. So these are the values of R pi and RE, and we will be using these for modeling. Now when I say about modeling, why do we need to model a transistor, and what is a model? A model can be defined as the combination of circuit elements, if properly chosen, that best approximates the actual behavior of a semiconductor device under specific operating conditions. Now, why do we need a combination of circuit elements? If we can model a device into some circuit elements like resistors and current sources or voltage sources, then doing analysis on them becomes easier. Like if you convert a transistor into its corresponding resistors and sources, then you can apply whatever you have learned in circuit theory on that. We use some tools for analysis. These tools can be mesh analysis, nodal analysis, or Thevenin's theorem. All these things can be applied on the transistor, which was not possible if there was no model. So modeling is important. So by doing modeling, we are actually reducing the complexity of problems. Okay. So let's do the modeling part. We'll start with pi model, then we'll go for T model. In this lecture, we are only considering that much, and in the upcoming lectures, we will see H parameter models and some problems. And after that, we will analyze different configurations of amplifiers, BJT amplifiers, using these parameter models. So let's draw the pi model. Here we have our transistor. This is the collector, base, and emitter. Now we are going to model this transistor into its equivalent circuit. Okay. Now it can be drawn as a resistor, a controlled source, which is a voltage controlled current source, and then a parallel resistance to the current source. So we have modeled this circuit as a two-port network. This is our input side. Here we have the resistance R pi. This is our voltage controlled current source, which is represented by GM VBE. Now here we have a resistance which is R out, the output resistance of this transistor. Now we know R pi, we have already derived an equation for R pi. This R pi is between base and emitter. So this is base, this is emitter, and this is collector. So the entire common terminal is emitter. Now through base IB flows, through emitter IE flows, and through collector IC flows. Now we know that VBE is equal to IB into R pi, right? That also means GM VBE, which is the voltage control current source, its value must be GM into IB into R pi. Okay. GM into R pi is beta. So this is beta into IB. That is almost equal to IC, but there is a condition. Condition is that R out must be a very high value, right? So far we haven't discussed what RO is. RO is obtained from the output characteristics of this BJT, and RO can be written as dou VCE divided by dou IC. It can also be written as modulus of VA divided by IC, where VA is called the early voltage. Now let's see what VA is. We know that this is the characteristics of a BJT, output characteristics. This is IC and this is VCE. So this is for constant IB. But we also know that the relation between IB and IC is a linear one. Then why is it increasing? If IB is a constant, IC should remain a constant. But if IC is increasing, the reason is because of early effect or base width modulation. We also know that this is a straight line. it has an exponential portion here. After that, this becomes a straight line. If we extrapolate this straight line, this will intersect with the x-axis at this point. If we take the voltage between this point and from where we started extrapolating, the modulus of the difference in this voltage is called the early voltage. This is VA. From the output characteristics, we can find out VA, and from that we can find out the value of RO. Now we have arrived at an equation that says GMVB is equal to beta into IB, which is, let's say, if this is equation 1, this is equation 2. So from equation 2, we can derive another equivalent circuit for this, which is a current controlled model. So that current controlled model will look like this. This is our R pi. Here we have a current controlled current source. And then the parallel resistance RO. Collector, emitter, base, and this current is beta IB. This is R pi R. So this is a current controlled current source model of BJT. This still comes under pi model. Okay, if I haven't said this before, BJT is a current control device. The output is controlled by the base current. If it is in common emitter configuration, the output is controlled by the base current. So BJT is a current control device. So this will be a more accurate model for BJT because this is IB and output is controlled by this input current. Here this model represents a voltage controlled current source. That means this current, this output is controlled by this voltage. This means this will be a more accurate equivalent model for BJT. Now we can discuss how a T model looks like. Here we have base. Here there is a resistance between base and emitter. Here we have the emitter, and there is a current source between these two. And here we have the collector. We have already derived an equation for this current source in our previous lecture, and this is alpha IE. This is IC, which is alpha IE. Here we will have IB, and here we will have IE. Now this resistance is the resistance when we look into the base emitter junction through emitter. What will be the value of this resistance? This will be RE. So this T model is also called RE model, and this is the model, the base, collector and emitter. Now we know that IE is equal to GMVB. So IC can be written as alpha into GM into VBE. So from this equivalent model can also be drawn with a voltage controlled current source. So that equivalent model will look like this. Base, emitter, there is VBE between base and emitter, we have RE here, this collector, this current source will have a value GM into VBE, and this is a model where we have a voltage controlled current source. Now we are in a position to carry out the analysis of, that is, small signal analysis of a BJT amplifier. Before getting into that, we need to prepare our amplifier circuit so that we can apply our equivalent circuit. That is, let's say we have an amplifier. This is a common emitter amplifier, looks like this. Now we know that this is VCC, this is R1, this is R2, this is RC, this is RE. We have already seen the circuit. This is the voltage divider bias for common emitter configuration. Now we have CI here, CO here, and CE here. This is our source, that is the signal Vs, and this is the resistance of that signal source, which is Rs. This is the internal resistance of this signal source. Now in small signal analysis, we are going to do the AC analysis of the system. Now there are two supplies in the system. One is this VCC, which is the DC power supply, and then there is this Vs, which is the small signal AC supply. Okay, so we are going to apply AC analysis. So this is our V in. Here we have our V in to the amplifier. For our particular application, for our particular frequency, we are assuming that this is a linear circuit. Okay, this holds for most of the frequencies or most of the operating conditions of this particular amplifier. So if this is linear, we can apply the superposition principle here, right? So there is a DC source and there is an AC source. We can separate them. We have already done the DC analysis of such circuits, so we know how to do that. Now we need to do the AC analysis. So in AC analysis, we are removing the DC sources. So this DC source will be connected to ground. And there are capacitors here. What happens to the capacitors? These capacitors are designed such that for lower frequencies, because we are now considering the low frequency small signal analysis. So for lower frequencies, these capacitors will offer lower reactances. So they are designed like that. So if these capacitors are considered to be lower reactances, that means we can approximate them into short circuits, right? So this becomes a short circuit, this becomes a short circuit, this also becomes a short circuit. Now the function of these capacitors are like that. This Ci will prevent the flow of DC current to this AC source. C out will prevent the flow of DC current to this output, so that we will get only the amplified AC signal at the output. And this CE is a bypass capacitor. This will bypass this resistance RE, so that only DC currents flow through RE, and during the operation of this amplifier, the current through RE does not change the operating point. If both AC and DC currents flow through RE, that will change the operating point. So in order to avoid that, we have CE, that is the bypass capacitor. So here we have a short circuit, here also we have a short circuit. So if we redraw this figure, it will look like this. Here is our transistor. Now this across this resistor RE, there is a short circuit, so we can draw it here. Emitter is directly connected to the ground. Now this is a short circuit, so this is directly connected to our output. So between ground and this point, we have our output. Now this RC has one of its end connected to the ground, because we have removed the DC supply, so this will be connected to ground. Now one end of R1 will also be connected to the ground. One end of R2 is also connected to the ground. This capacitor is short circuited, that is Ci is short circuited. Here we have Rs, and here we have our source. Now the source is Vs and this is Rs. Now let's see what happens. This is now ready. We have prepared the transistor for small signal analysis. Now we can apply our model. Whatever model we want to select for our BJT can be applied here. So this circuit becomes like this. This is Vs, Rs, R1, R2. Here this is Rc. Let me draw it here also, denote them, Rc. Now across this point we have our output. Across this point we have our Vi. Now this box can be replaced by the transistor model. So here this model can be anything. It can be this pi model we have derived, it can be this t model we have derived, it can also be the h parameter model we are going to discuss later. Here the circuit will have the base of the transistor, here it is collector, and here there will be emitter, and emitter is connected to the ground. So this is our transistor model. So replace this box by the transistor model, and now we can do the small signal analysis. Okay, so let's do the small signal analysis for this circuit itself. And before getting into that, we need to see one more thing, and those are some important parameters. So whenever we do small signal analysis, we need to find out these parameters. So we know that we are going to model all our transistors as two-port networks. So I am going to represent a two-port network here. This is our two-port network. This is the input terminals, and this is the output terminals. Here we will have plus or minus Vi, the current going in, which is II. Here also we will have IO, the output current, and here we will have VO. When we look into this two-port network, we will see an impedance. That impedance is called Zi, the input impedance. When we look from the output side to the two-port network, we will see an impedance. That impedance is called Z out, or the output impedance. Okay, so this is our system, two-port network, and we have already learned how to model our transistors as two-port networks. So the first parameter is input impedance. Denoted by Zi, and Zi is given by Vi divided by II. Now this value cannot be found out by an ohmmeter, because we know that ohmmeters use DC supplies. If we have a source in the system, let's say this is our source, there is the source resistance Rs, then there is our two-port network, If this is the case, we need to avoid this when we find out the input impedance. We need to look from here and try to see the impedance after the source resistance. Here across this we will have Vi, and towards the input terminal we will have Ii. Okay, so we will start looking at the transistor after the source resistance, that is exactly at the input of the transistor. So this is input impedance. Now the next parameter is called output impedance. Denoted by ZO. Now ZO is given by VO divided by IO, that is the output voltage divided by output current, but there is a condition when input is short circuited. Or we can say that when there is no input and there is no signal. So this is output impedance, and to find out output impedance, we are looking at the transistor from the output terminals. Now the third parameter is called voltage gain. It is denoted by AV. The voltage gain AV is defined as output voltage divided by input voltage. And in our analysis, this AV is called the small signal voltage gain, because we are doing the small signal analysis. So the fourth parameter is called current gain, AI. Current gain is defined as AI is equal to output current divided by input current. And in case of BJTs, we know that in accordance with different configurations, AI can be very close to 1 or a very large value which can be even more than 100. So these are the 4 parameters, 4 important parameters when we are doing a small signal analysis of a BJT amplifier. Okay, now can we start the analysis? Let's go. We'll do the analysis of common emitter amplifier with bypass capacitor. We already have the circuit diagram for that. This is it. Now we know that this is VCC, this is RC, this is CO, this is RE, this is CE, this is R2, this is R1, this is CI, RS and VS. This is our base, collector and emitter. Let's say there is a load resistance here, and this is RL, and across this load resistance RL we have our Vout. Now we have already prepared this circuit for small signal analysis. Let's look at that. So this was our final circuit. Now we have to insert a transistor model here. We can use any model we have already seen. We can use T model, we can use pi model, and for this analysis we are going to use the pi model. Okay, so I am replacing this box by the pi model, and I am also doing one more thing. That thing is I am combining this R1 and R2 because you can see that they are in parallel. So I am joining this into their parallel combination. So our equivalent circuit will look like this. We have our Vs, then there is our Rs, then the parallel combination of R1 and R2, and from here, and that parallel combination is connected to base. From here our equivalent circuit starts. There is R pi, then there is the current source, which is the voltage controlled current source, Gm into VBE, and the output resistance R out. Now this is the base, this is the emitter, and this is the collector. At collector we have two resistance, one is RC and the other one is RL. This is all connected to the ground. Here also let me replace this with ground. Anyway it is connected to ground, but do this more accurate. Here we have the output. Now this is RS, this is VS, this is R1 parallel R2, this is RO, RC and RL. Now here we have our V in, Vi, and this voltage controlled current sources GM VBE. So now our equivalent circuit, that is the equivalent circuit of this entire diagram, is this one. Okay. Now we can identify the input and output resistances. This is our input point, this is our input terminal. So what we get from looking here is the input resistance Rn, and this is the input of our transistor. So here we will have Rin dash. If you look at the transistor from these output terminals, you will see RO dash, and if you look at it from here, you will see RO. Okay. Now let's say RL dash, which is when we look at this from this output terminals, is equal to RL parallel RC parallel RO. Then let's say RB is equal to R1 parallel R2, the combination of this parallel resistance. Now we can redraw this circuit again, and that will look like this. We have our Vs here, Rs here, Rb here, then R pi, this is the input side. Then here we have our GM into VBE, and the resistance RL dash. This is GM VBE, this is RL dash, and here we have our output. This is R pi, this is RB, and this is RS, and also this is VS. Now we can write the gain of this amplifier, which is AV, which is equal to V out divided by V in, where V in is nothing but VBE. So the voltage gain of this amplifier on part only is AV equal to V out divided by VBE, and the voltage gain of the entire system, which is AVS, is equal to V out divided by Vs, because we are giving Vs as the input, but some part of that input is dropped in the Rs resistance. So if we consider the amplifier, V in is its input, which is equal to VBE. But if you consider the entire system, Vs is the input and V out is the output. Okay. Now we know that a current IL flows here in RL. So if we equate that current to GMVBE, if you consider the directions, IL will be equal to minus GMVBE. Now if you look here, we know that IB flows here, and if you look at the output, we know that V out is now equal to IL into RL dash, and we already got IL, which is equal to minus GMVBE, and that into RL dash. Now from this equation, we can write the value of AV, which is the voltage gain, which will be equal to V out divided by VBE, which is equal to minus GM into RL dash. So this is our first parameter, AV. Okay. Now let's say we are neglecting early effect. So neglecting early effect, this means R out is equal to infinity, because without early effect in the output characteristics IC will remain a constant. That means R out will be equal to infinity. That will make RL dash equal to RC parallel RL. Therefore, AV becomes minus GM into RC parallel RL. If the output of this amplifier is open circuited, that is, if we are not connecting any load resistance here, that means RL dash will be equal to RC only. So if RL is equal to infinity, that means the amplifier is open circuited. In that case, AV will be equal to minus GM into RC. So for many of the problems, you can apply this approximations. Now the voltage gain of the entire system AVS, we know that it is V out divided by Vs. Now this can be written as V out divided by VBE into VBE divided by Vs. Now we know what is V out divided by VBE, which is equal to AV. So this becomes AV into VBE divided by Vs. Now VBE can be written in terms of Vs. If you look here, this is VBE, which is across a parallel combination of RB and R pi. So this, I am only redrawing the input part. It can be redrawn as, here we have Vs, then Rs, and one more resistance. This resistance is RB parallel R pi. This is Rs, this is Vs. Across this we have VBE. Now we can write VBE as Vs into RB parallel R pi divided by Rs plus RB parallel R pi. Now this can be substituted here. So we will get AVS as AV into RB parallel R pi divided by Rs plus RB parallel R pi. So this is the value of voltage gain of the entire system. Now we can find out the input resistance of this configuration or this amplifier. Because in case of a BJT amplifier, the input impedance is only going to be resistive. So this is input resistance. So we know that input resistance is, when we are looking from here, sorry, this is Rin and this is Rin dash. So the input resistance Rin is when we are looking at the transistor from this point onwards. That means here we have a voltage drop VBE and a current is flowing, which is IB. So Rin can be written as VBE divided by IB, which is equal to R pi only. Now we can also write Rin dash. If you look at the figure, you can see that Rin dash is nothing but the parallel combination of these three resistances. That is these two resistances. That is R1 parallel R2 parallel R pi. Now for the output resistance, which is R out. R out is equal to, when you look here, this is R out. In R out, we can see only R0, that is small r out, right? So R out is equal to small r out. And here we have another output resistance which is called Rout dash, is by finding out the open circuit voltage at the output and short circuit current at the output. And in this case, Rout dash is given as RC parallel RO. And the last parameter is current gain. Denoted by AI. AI is equal to I out divided by I in. We know that I in is IB and IL is
minus
GMVBE
minus
GMVBE divided by IB. VBE by IB is R pi, so AV is GM into R pi. And we also know that R pi is beta divided by GM, so this becomes GM into beta divided by GM, which is equal to
minus
beta. This is the current gain of this amplifier. Okay, we will analyze more circuit in the upcoming classes with more models of transistors. And for now, this is enough. I'll be winding up here. We'll meet again. Until then,